Introduction. Relative density principles applied to compaction of relatively clean, coarse-grained soils. Relatively clean, coarse-grained soil usually means less than 15% fines. Compaction tests are not commonly performed on soils within 15% or fewer fines. A small percentage of fines means soil cannot easily hold water to examine range of water and effect on dry density. Relative density can be found by the equation given below. To find the relative density, maximum density, minimum density, and field density values are needed. Minimum index density can be found by using following methods. 1. Method A. Using a funnel pouring device or a hand scoop to place material in mold. 2. Method B. Depositing material into a mold by extracting a soil-filled tube. 3. Method C. Depositing material by inverting a graduated cylinder. Field density. Direct methods. Sand cone method. Nuclear method. Drive cylinder method. Sleeve method. Sand replacement method. Water replacement method. Time domain reflectometry. Indirect methods. DCP. Dynamic cone penetration. SPT. Standard penetration test. According to the relative density values, soil can be classified using the chart given below. Scope of the test. This test is performed to determine the relative density of cohesionless, free-draining soil using a vibrating table. The relative density of a soil is the ratio expressed as a percentage of the difference between the maximum index void ratio and the field void ratio of the cohesionless, free-draining soil to the difference between its maximum and minimum index void ratios. Standard references: ASTM D4254 Standard test methods for maximum index density and unit weight of soils and calculation of relative density. ASTM D4253 Standard test method for maximum index density and unit weight of soils using a vibratory table. Significance: relative density and percent compaction are commonly used for evaluating the state of compactness of a given soil mass. The engineering properties such as shear strength, compressibility, and permeability of a given soil depend on the level of compaction. Equipment: vibrating table, mold assembly consisting of standard mold, guide slips, surcharge base plate, surcharge weights, surcharge base plate handle, dial indicator gauge, balance, scope, straight edge. Test procedure: minimum density index. 1. Fill the mold with the soil approximately 0.5 inch to 1 inch above the top of the mold as loosely as possible by pouring the soil using a scoop or a pouring device. Funnel spiraling motion should be just sufficient to minimize particle segregation. 2. Trim off the excess soil level with the top by carefully trimming the soil surface with a straight edge. 3. After filling the mold, excess soil is carefully scraped off. Knowing the weight of soil in the mold, MS1, the dry density is easily computed. Maximum density index. 1. Again fill the mold with soil. Do not use the same soil used in step 1 and level the surface of the soil by using a scoop or pouring device funnel in order to minimize the soil segregation. The sides of the mold may be stuck a few minutes using a metal bar or rubber hammer to settle the soil so that the surcharge base plate can be easily placed into position and there is no surge of air from the mold when vibration is initiated. 2. Place the surcharge base plate on the surface of the soil and twist it slightly several times so that it is placed firmly and uniformly in contact with the surface of the soil. Remove the surcharge base plate handle. 3. Attach the mold to the vibrating table. 4. Vibrate the mold assembly and soil specimen for 10 minutes. 5. Determine and record the mass of the mold and soil MS2. 6. Determine the decrease height H dash of the soil to compute the decreased volume of the soil. 7. Empty the mold and determine the weight of the mold. 8. Determine and record the dimensions of the mold, that is diameter D and height H. in order to calculate the calibrated volume of the mold Vc.